We start the last session of this morning.
Yes. Thank you very much indeed. Yes, my talk is about the title that you see here, the interpretation of quantum mechanics, often considered a rather esoteric aspect of science, not really worth looking at. That I will try to explain why. Nevertheless, it is very important to do these things right. I saw many colleagues saying they are agnostic. They don't care about how to interpret quantum mechanics. As long as it works, it's fine for them. Well, to me, that sounds just like scientists from the 19th century saying they were agnostic about the existence of atoms. Atoms were too small to be observed, period, they're going to do something else. Clearly, atoms were very important in those days, and they determined how the rest of science developed ever after. So similarly, I think the interpretation of quantum mechanics is very important to get it right, and that includes the interpretation of other theories such as general relativity as well. If you can go to my second slide. Yes, so I'll start with a rather long introduction to show how things happened in the past. So similarly, Isaac Newton was one of the first modern scientists in the sense that he quantitatively investigated the laws of the forces between things, and he discovered something even more important than Newton's laws itself. He discovered that what happened in the heavens is controlled by the same laws of physics as it happens on the ground. If you drop an apple from this high just to see what it does, the equations for that are the same equations that control how the moon goes around the Earth. And that is a very important observation. Next slide. The next step was when James Maxwell wrote down the Maxwell equations. He made another such unification, discovering that the laws of electric fields and the laws of magnetic fields are basically almost identical. They are part of one unique branch of science, electromagnetism. And once you saw that, one could very soon realize that everything having to do with light is controlled by the same equations as well. So as soon as you unify certain notions of physics, you discover new things. I'm going to say the same thing about the interpretation of quantum mechanics itself. Next slide shows that Einstein's theory of special relativity, that theory really combines Maxwell's theory with theories of matter. Why I'm saying that? Well, E equals mc squared is Einstein's famous formula, but E and m are properties of matter, whereas C is a property of light. So to see that the properties of light and the property of matter are controlled, are linked by similar equations was a very important advance. Next slide shows that I'm going to modern science, and we see that one of the first things that happened in the beginning of the 20th century was special relativity. Einstein discovering that you have to combine the laws of relativity as he saw them before, but then apply that to the properties of matter and the properties of those very tiny atoms that could also be shown to have a real significance in physics and are controlled by, again, very similar equations. Modern science then continued by producing the standard model of the elementary particles. Next slide. I want to add to the standard model that was one of the very deep and fundamental successes of the 20th century. Very quantitatively, very detailed, it described how atoms and particles interact, what kind of forces there are. Now, that leaves us with the gravitational force. science started with gravity by Newton's laws of the gravitational force just being inversely proportional to the distance. But gravity came back as a last ingredient of modern science as well. Einstein discovering general relativity, the fact that gravity has to do with curvature of space and time. So actually gravity acts as a law that's particularly relevant, valid for very large things in the universe. So typically planets, stars, galaxies, even universes themselves are very dominantly controlled by the gravitational force. And gravity could be linked to the fact that space and time are actually curved. The next slide is that again, also for gravity, if you add two theories together, you might discover more. So the standard model is not complete, and we see that the elementary forces, how they act on elementary particles, but the inclusion of gravity as it acts on very small particles doesn't work very well. So gravity is particularly suited to describe big things, but it doesn't work so well if you want to understand how particles themselves act on gravity. Now you could argue that the gravitational force for individual particles is so tremendously weak that it's never of any real practical use, but that means that there's a branch of science that we don't understand, and in particular we cannot do any experiments in it, which is how gravity acts on individual particles. That is a famous problem of quantum gravity, and at the same time that we say this, we realize that we have a gap in our understanding, and considering all these past experiences I told you about, it seems to be natural to believe that once we fill that gap, once we figure out exactly how to write down the right equations for the gravitational force as it acts on elementary particles, we will discover many new things. So this is the rationale for being very much interested, even in a branch of science where no direct experiments seem to be possible. I think indirect experiments are possible to a large scale, because if we do this right, we will probably understand why the standard model has the structure that has been observed today. But there are many mysteries as to what the values of the coupling strengths are, what the spectrum of elementary particles exactly is. The standard model tells you only if you see the spectrum, then you can do these calculations. But where the spectrum itself comes from is still a mystery. That is something that we should try to solve. And in the next slide, slide number 9, next slide, please. The most remarkable thing that gravity does in general when you have lots of matter is the formation of black holes. Black holes seem to be peculiar features of general relativity itself, and they look like the hydrogen atoms of general relativity. If we understand those, we will understand very many other things. As Stephen Hawking said, he wanted to understand God's ways, what God had in mind when he wanted to create the world. And so I totally agree with Hawking at this point, that what you have to do to understand how gravity works, even how it works on elementary particles, is to study black holes. Black holes, as I said, are born when stars collapse under their own weight, and the solution that you have to look at is a solution that was already immediately found shortly after Einstein formulated his theory. A solution was found by Carl Schwarzschild, saying that if you assume perfectly spherical symmetry, you can write down in a closed form the solution of these equations. And that solution was what we now call a black hole, but had many more features that are extremely interesting and spectacular, actually. So that if you understand these things right, you might learn many new things about nature. You might learn about something that's hidden behind or inside a black hole. What is it? What are the laws that control nature in those domains? That started out as a big mystery, but maybe if we add the properties of elementary particles to black holes, we can solve those problems. Yes, so yes, please go to the next slide then. So according to general relativity, when particles fall into a black hole, they'll never be able to get out anymore. But that was when you didn't take into account quantum mechanics. And it was Stephen Hawking himself again who did that exercise. He said, quantum mechanics tells you how particles behave when they come close to the black hole. And we have the equations for that. So why not try to solve those equations? So again, make a step as significant and important as Carl Schwarzschild did when he first discovered black holes, was also what Stephen Hawking did when he added quantum mechanics to the features of a black hole. Because that gave as a surprising result, totally unexpected for many people, including Hawking himself, it gave as a result that black holes actually radiate. Particles can fall in, yes, but they can also come out. And that was fantastic because these particles that come out are only come out because of the laws of quantum mechanics that are applicable to them. It doesn't matter where they are in the standard model. The only thing that matters is their weight and their energies. And then the number of particles of that kind that come out is the same as the number of any other particles coming out of the black hole. So the black hole makes no distinction between members of the standard model. And that's already something very peculiar and very interesting that was found here and suggests that there is something we don't understand about nature. Because normally speaking, we would say neutrinos are invisible and other particles will be very rare, other particles will be very common, but no, what comes out of the black hole is uniform. And that was according to Hawking's calculation. But I'll argue later that there was something about Hawking's calculation that he implicitly made some assumptions which might actually not be true. But that is again because we have, as I argued earlier, you have to combine different fields of science together, but you have to do that right. And doing it right is very far from trivial. And even if you got all the equations, you can still solve them in the wrong way. And that's what I claim, but that comes later in my talk. Go to the next slide. This was actually where I argue that black holes handle all the particles in the same way. But the question one can pose at this point is, did Hawking discover something new? Did Hawking discover something about the divine laws of physics that we are dealing with today? What was it? Go to slide 12. There was a peculiar problem, not so much realized by many scientists. The problem was that you have no way to do experiments. We know the equations, we know how to solve them, but we don't know exactly what they say and why. So it looks as if the particles coming out of a black hole, each particle separately comes out from one separate place on the horizon. The horizon of the black hole is a mathematical surface that you can write down in the shape of a sphere. And what is inside the sphere is invisible to the outside observer. What's outside the sphere can be described by equations that we know. So that was something that new that we learned about equations and about space and time. Particles come out at distinct points in space and time. Next slide. But what happens there exactly? By moving around the way they do, the particles seem to transmit messages from the particles that fell in. The difficulty that people arrived at was that there are particles falling into the black hole, there are particles coming out of a black hole, but in ordinary subjects of physics, the things that come out are always related to the things that went in. So if you take a bucket of water, you pour more water into the bucket, then what flows over the edge depends on what you throw in. And it holds not only for buckets of water, it holds for atoms and molecules, it holds for stars and planets. Every physical object has the property that you can do something to it, but it will react. Now, it looked as if the black hole will not react. The particles that come out of the black hole will not depend on the particles that you threw in. That was at least the outcome of Hawking's calculation. But the question one can ask is, was that correct or not? Or are there more subtleties that we don't understand? If there are subtleties that we don't understand, they have to do with the interpretation of quantum mechanics. Slide 14, please. So our understanding of nature seemed to be incomplete. And that is the same kind of incompleteness that Einstein and Bohr and Heisenberg hit upon when they first discovered quantum mechanics. There was something missing in the description. But it was very similar to the problems of those early days, that quantum mechanics seemed to be incomplete. And people found answers, at least answers they thought are pretty obvious, and you can use them to continue your research of science by saying that although the answers are incomplete, they are all you need. That was the general Copenhagen conclusion about quantum mechanics. Don't be bothered by the incompleteness of your view of what actually is happening. Just realize that you found all the equations needed to explain the outcome of your experiments. And now something very similar seems to happen. The particles coming out of a black hole do not relate to the particles you threw in. You might be worried about that, but you might also say, well, isn't that nice? That's what my equations say. Let's continue and see what else we can derive about black holes. Well, actually, I think that we should not have skipped that phase of our investigation, just like we should not have skipped the phase of the investigation of quantum mechanics itself, where people say that even if your equations seem to be incomplete, you should be happy with what you have and don't be worried. So now, to understand better behavior of space and time and matter, is that we have to be worried again about those questions which we thought had been finished in the earlier days. It's actually not true. So next slide. The questions seem to be philosophical ones. And as it is often the case with philosophical questions, the answers that people tend to give are dependent on the culture they live in. And so the Western world may have different answers to the questions of what happens inside a black hole than people from Asia or Africa. They all have different answers because their cultures are different. But that, of course, shouldn't be the case in science. If you finally agree about what's happening, then we should get a universal answer, as these are the equations you have to solve. The equations really tell you everything you ever want to know, and those will be the answers. So in quantum mechanics, one also started to ask the questions as to what the quantum formulas are exactly telling us about these particles and how they move, and what happens when they collide to other particles. Next slide. This is a repetition of what I already said, that Einstein was the father of the forces of relativity on the one hand, and Niels Bohr and Werner Heisenberg and many others were the quantum mechanics investigators on the other hand, and they didn't quite agree with what was found. So now we are 100 years later, and this discussion, the Einstein versus Bohr and Heisenberg, this discussion was almost subdued, was almost finished. But in modern findings about black holes, about the universe, about cosmology, we again have to go back and investigate these disagreements one had in the past. Did he indeed find the right answers or not? My claim is no. The answers that were popular for the last 20 or 30 years or so may have to be revised again. So we have to unearth the answers given 100 years ago nearly by many people and say, no, we have to find more precise answers. So there's the issue of free will. Next slide. There is a peculiar phenomenon in quantum mechanics. If you try to understand what happens when a certain experiment is being done, there's a famous Bell experiment. I won't go into the details of what the Bell experiment really was about, but it was about a particular setup of particles that were being studied. And now the answers that the experiment gave depend on the settings of some detector apparatus. The detector apparatus measures the polarization of light coming out of the system, and what came out of the experiments depended on the detectors settings that were using, and the detectors could be set by the experimenter's free will. He had the freedom to put the detector in any particular position and then ask what comes out. But depending on what they did by free will, the result of the experiment became different. And the most natural answer seemed to be that if the observer, whenever the observer makes a change in his settings, that observer will act out of free will only apparently. In reality, the actions of the observer are not determined by his free will, but determined by the laws of physics. And that is revolutionary, because one would have thought that our mind is in some sense above the laws of nature. If we decide to put the settings in this way or in that way, shouldn't matter when you do an observation. But it turns out that whatever you do you can only be giving answers that you understand if you assume those settings to be determined by the laws of nature in the past, the laws of nature that made the particles move the way they do when you start the experiment. This is again revolutionary and very disturbing to many scientists, because they thought if you do an experiment, you have the freedom to choose settings any way you like. That shouldn't depend on what laws of physics particles in the past were following. But the answer of some other physicists, including myself, is that of course the results do depend on the settings, on the particles, whatever they did in the past, because all the laws of nature are coherent. Quantum mechanics is not the theory that many people think it is, which is that it transcends the logic of cause and effect. It replaces those laws by laws that handle probabilities and distributions. And because of that, you can reintroduce the notion of free will for an observer in your description of the law of what happens when you do an experiment. But that is too premature a conclusion. Next slide, just briefly. Once you make your decision, you cannot measure anything else due to the elusive behavior of those particles. Yes, go to slide 20, please. Next slide. Yeah, John Bell was one of the scientists who proposed this Gedanken experiment. What he did is something very important because he showed that it makes a difference whether or not you assume that an observer can choose the settings of his machines independently of whatever happened in the past. Now, quantum mechanics then gives a very confusing answer unless you assume that the settings chosen by the experiments did depend on laws of nature in the past. So up till shortly, most scientists immediately sided with Bell and Bohr and Heisenberg, and not with Einstein. Einstein said there's something wrong here. You have to have cause and effect in scientific equations. So nowadays we have been reconsidering all these findings, and we reach a different approach. The differences seem to be innocent, and it seems to be just a question of whatever your religion you are following, which should have no effect on the science equations that you're trying to solve. But no, it does. Next slide. The photons that are coming out of the light source are entangled, and you can have two experimenters, Alice and Bob, who make measurements of their choice, each on another photon, and the question is how the photon will be polarized. What polarization do they find? And how are the findings by the two observers called Alice and Bob, just for the A and the B, how are these findings correlated? So on the next slide, that was the reaction of scientists during most part of the previous century, and most of today's time also, that the erratic behavior of photons, the correlations that Bob and Alice find, were calculated too big to give Einstein to agree with what Einstein was saying. So Bohr and others had to be right, and Einstein had to be wrong. Yes, go to slide 23. So that was because the scientists assumed that Bob and Alice had free will. But now we say, no, it's not. And the answers for our next theories, particularly about particles near black holes, are going to depend on that, strangely enough. So go to the next slide. Bell had made that conclusion that free will had to be allowed for the observers, but Bell had made assumptions. And if you deny the fact that Bob and Alice were doing things that are independent of the positions of particles in the past, then you get the quantum mechanical answers. But if you say that what Bob and Alice did was dependent on the past, then you could explain the observations, but you would deny the free will, and that would not be allowed. Let me go to the next slide. And give me the next slide, please. Yes. So what about it? What about gravitation? And the peculiar thing is that here a similar dispute might emerge. Stephen Hawking computed the radiation that emerges from black holes. And he used as a starting point that are not so dissimilar from what Bell actually did. So he assumed that particles inside the black hole can do anything. They are uncontrollable by us. They cannot be affected by the particles outside. So the horizon of a black hole really separates two universes, a universe of things inside the black hole and a universe of things outside the black hole. Only the things outside the black hole could be controlled by us. What happens inside is controlled by some free will that the black hole seem to obey. And that was in line with this idea of the existence of other universes. The black hole seemed to be a wormhole connecting one universe to another. So what happens in that other universe determines the behavior of particles inside the black hole. Those particles may come out, but what then comes out of the black hole depends on what happened in this other universe. And many people were happy with that, particularly Stephen Hawking loved the idea of a famous movie star jumping out of the black hole, sitting on his lap. He made a Photoshop picture of himself that way. But this kind of erratic behavior doesn't seem to be scientifically very satisfactory, at least not to me. So next slide. Particles that went inside cannot be measured. The information that they carried seemed to get lost. And this was not disturbing Hawking at all. He thought, well, this just puts some divine arbitrariness in the laws of nature, which he liked very much. But it seems to be standing in our way now to understand what black holes really do. Next slide. If particles behave the way I suspect, they actually radiate differently from what Hawking claimed that he had to have found. In my calculation, particles never go inside the black hole. They touch the horizon, but only at infinite amount of time. The inside of the black hole is actually empty. There's not even particles, not even information inside. There's just nothing inside. This would imply that the black hole radiation would not be what most people say today and what Hawking derived, but it will be radiation according to a temperature, but that temperature will be twice the temperature calculated by Hawking. So now I'm in disagreement about a factor 2 in my calculations, and the question is, who's right now here? And this could be something to be checked experimentally. It's just very unfortunate that black holes are so small. Black holes which radiate at all must be very, very small, and such small black holes cannot be observed, not even by radio telescopes divided over the entire Earth. They could actually look at very large black holes that way, but they cannot look at small black holes. So the experimental information is completely absent. We have to do with thinking about these things, just like on the previous talk by Mrs. Nelson Jones, that in the distant we can only observe very large black holes and not the small ones. So it's unlikely that Hawking radiation can ever be detected for microscopic black holes because they would have to be very close to us. But such black holes have never been detected. There's no indication whatsoever that such black holes exist in any reasonable quantity to be able to study them. That's too bad to do this. What we have to do is, in fact, we have to think. And so our thinking has to be sharpened. And this is a real difficulty that the questions raised at first sight seem to be entirely philosophical. But the answers that most researchers primarily find is answers given by some philosophy. And then they only think that they've understood God's way. But for myself, at my side, I think that the kind of God that I would believe in to have generated laws of nature, that God is much, much more mathematical and works with closed equations, doesn't work with arbitrariness, doesn't work with free will or anything like that. It just has complete control of what happens in the universe. It will not be easy to find out who is right, but I believe most in this kind of logic. Oh, you haven't shown me the last slide. Please give me the last slide. Yes, and the next one. Right. So This terminates my talk. Thank you very much. I don't hear anything.
Okay. There is Professor Settimo who has a question for you.
Yes.
I'm not yet professor. I hope so soon. But yes, I'm from the University of Nottingham. Thank you so much for your presentation. The question I would like to ask, we have been in contact after your conference in Padua, and I also ask you about how you see the laws of nature, the physical law. So you had a word sometimes in a presentation where you said that the law of nature seemed to be incomplete, and there seems to be, you almost have a desire to find a law which we haven't yet grasped. So I would like that you comment this, and also in light of the fact that there is evidence that sometimes constant of the physical laws can change, for example, with some measure from distant young quasar. You remember I mentioned that also the Dirac had that hypothesis that the constant of gravitation could change. So is your view that there are statistical laws that we haven't discovered yet and that you want to discover? And the very last question, how much are you driven by the beauty of a physical law? And I'm thinking sometimes the Eddington attitude towards the gravitational law, that is so that Einstein formula were actually beautiful, and that play a big part for his development of the physical law. So I just wonder your view of the physical law, whether it is there to be discovered, or is it something that you, yeah, how you see this problem? Thank you very much.
Well, you are asking a lot of questions. I still was following one of the last seminars that Dirac was giving about his ideas of constants of nature being not stationary in time, but actually being variable in time. The problem with that, as I always saw, is that that means that the laws of nature depend on something, and the question is, how do they depend on time? What controls now their value? And that would mean that the value of certain constants, or more precisely, the ratios of constants, like the ratio of the mass of the electron and the mass of the proton, numbers like that, or the fine structure constant, which is also a dimensionless number. These dimensionless numbers somehow depend on space and time. But then my immediate question is how? What controls that? What are the equations? Are those fields in space-time, fields that we never observed for whatever reason? I find that very mysterious. So to my taste, Dirac is adding more problems than answering, than solving with his hypothesis. It seems much more natural to believe, but it is a belief, that laws of nature are constant. At least that would make things make it possible for us to really understand things in nature, whereas having space-time dependent laws puts us a big step backwards. Now, that's not an argument to say why it is wrong. So maybe Dirac was right, but there's something else, which is the experimental observations. Many of his assertions could now actually be checked experimentally. For instance, with a spacecraft on the moon, they can measure the distance between Earth and Moon up to a few centimeters accurate, and that distance would change if the laws of nature would change as a function of time, and that could be measured. And actually, they found no, there's no such change. At least within reasonable accuracy, scientists have not found the kind of change that Dirac would have predicted for such numbers. So the observations are on the side of constants being truly constants. I would also favor that scenario, and that would be the first scenario for me to investigate, which again doesn't mean that that's right. Maybe Dirac was right, but there's no evidence for it, and I don't think it simplifies things a lot when you assume that that's the way nature behaves. And then, of course, there's what you asked about the beauty of science, of science equations. And there I fully side with Einstein. He discovered that what he found was beautiful. And that seems to be a universal feature in our science. I think that in time of Johannes Kepler, what he found about the orbits of planets was beautiful. All planets move in ellipses. How can you have that any way better than that? So that was a beautiful result. And Newton's laws saying that the moon behaves with the same laws as an apple when you drop it out of your hand, that is also beautiful. So quite generally, there seems to be a law that if a theory is obviously right, then people will see the beauty of it by itself as well. Yes, the correct theory of science are often beautiful. However, the question is about the converse. If someone comes with a beautiful theory, is it therefore correct? And then my answer is very often not, because scientists don't have the kind of imagination that nature itself has. There's equations which are more beautiful than we can imagine. So I think that the laws that will link the gravitational force to quantum mechanics will be very beautiful laws. The big question is which. I can imagine many beautiful systems, but none of them will be true because it doesn't work. So the ultimate beauty of the equations is perhaps not that the equations are nice and they fit on a small piece of paper, but the beauty comes when it turns out that they agree with everything else we know about the universe, that they bring about new kinds of knowledge and understanding. For instance, Maxwell understanding electricity and magnetism. Maxwell at the same time discovered that light also obeys the same equations. That's beautiful. And it's that kind of beauty that I hope to see more in the future. And I'm optimistic. I think we haven't reached the end of science yet, not by a long shot. So there will be many beautiful things waiting for us to be discovered, I think.
Okay, there is a question by Dr. Tam, Vincenzo Tam. So please.
Can you hear me? Okay. Yes. Oh, so first of all, thank you, Professor Ruft, a very nice talk. So I am I work in the University of Portsmouth, and I'm very much interested. Here I direct a hub in quantum science and technology, but very interested in the fundamental understanding of quantum mechanics and how that interface with gravity. But mostly, I think one question, I guess, that for me is interesting is. I mean, I believe, as you were saying, that eventually we may be able to find beautiful laws, mathematical laws that describe the quantum world and gravity, maybe in an harmonic way. What is your understanding of the actual ontological reason of these laws? Where do they come from? And because you were speaking also a lot about the connection with free will, so I would be really interested to understand what is your perspective. So the fact that we, I mean, as scientists, we long for understanding the universe and the mathematical structure, the harmony within it, its intelligibility. Where there are certain particular laws, where do they come from, and what is if there is any connection with free will, or so what is your perspective?
Well, I wish I could answer such questions. And the question, where does a law come from, is probably the most difficult question you can ask, because that suggests there's something lying underneath all these theories. There's quantum mechanics, there's general and special relativity, and there's quantum field theory describing the standard model and all the particles. It was hard enough for us, for scientists in general, to discover those laws, but it will be still harder to discover where they come from. You can only say that if you now look at what we found, you can say it logically fits better than anything we could have hoped for in the past. So you could say, as a suggestive possible answer to the question, is the logic that everything should be coherent. All the behavior of all sorts of particles, stars, planets, and materials, they should all hang together by equations that fit together, that make one beautiful, unified notion. And the demand of having such, if you think loud enough, hard enough about what kind of universe would we like to sit in, what kind of equation should such a universe obey? Well, the one answer one can think of is they should obey all the equations that make everything move in a systematic, understandable way. If you make that as a requirement, then you often find the universe couldn't have been much different from what it is now, because whatever creator is, I used to have a science teacher who was talking about the creator, where other people would say God or so. Whatever God had in mind, he was trying to make a universe tick like a machine, and every part of the machine should work according to the same equations. That's very hard. If I would ask you make such a universe, you would find how difficult it is to make a universe with so many intricate structures in it, and nevertheless all equations being related. That's very hard. So making such a law perhaps gives you one single unique law, and that could possibly be an answer to your question. But again, I'm not sure of this. This is just a guess.
But this single unique law, it's at the end has to have even it an ontological reason. Needs to come from something. So it would be an intelligible being that is behind it, or what is your?
I can give you one example of a model of a universe which doesn't look like ours at all, but maybe that's only because of our lack of imagination today. I consider this the set of prime numbers, all the prime numbers, so just number theory, period. So number theory could be our universe if I arrange all the prime numbers, but I arrange them in the form of quaternions. Mm-hmm. So quaternions will make the space of prime numbers four-dimensional, whereas one dimension is different from the others, which is the radial dimension. If you have them in quaternions, the small quaternions are sitting in the center, the larger quaternions will be sitting further out. But the larger quaternions are determined by the smaller ones in their properties. So if you look at the world of quaternions very carefully, it looks a little bit like our universe, our expanding universe. There's an infinite number of numbers, so they never stop. But the relation between the numbers in the quaternions are somehow controlled by laws of mathematics.
Yes.
That we know pretty well in the case of quaternions, but not at all well enough to make this a model of our universe. So I like to think of our universe as being something like what you get in number theory. Mm-hmm. But that's just a wild guess, and it could be completely wrong. So just to name you something that looks like the kind of universe that I would ultimately believe we might be sitting in.
Mm-hmm. Thank you. Yeah, that's interesting. And how that you connect that? Is there any connection with free will, or what is your perspective in that?
Well, that ultimately there is no such thing as free will. All our actions, either whether they are mental or physical or whatever, are all controlled by laws of nature. You know, if you walk, you move around because your legs are moving and so on. All that is just simple dynamics. But then what you're thinking is mental dynamics is much harder, but it's not different from the dynamics of the material objects. So that means there's no, strictly speaking, there's no free will, but there's also no reason to be concerned about that. Many people got upset when you can say there's no free will. They get very upset. They say, I want to think what I think, and I'm not going to be controlled by any laws of nature that I know of. No, you're not. But what are you controlled of? What is it that made you believe this or that, or made you decide upon this and decide upon that? There's something preceding that. And so particularly brain surgeons, brain specialists say, no, even our human brain reacts on things, on the stimulus it gets from the outside. So it doesn't think independently of what happens to it. And so there is no free will in that sense. But you shouldn't be worried about that, because you are the only one with the brain in which these decisions that you are making are being formed, and
Yes.
are not formed from a distance. So
Yes.
all the signals come through your ears and your eyes and your nose to your system, and those depend on what you think, and not those are the origins of what you think, and nothing else. So in that sense, you have free will.
Yeah, no,
From a pure physical point of view, you don't.
I see. So what you're saying is that what we do affects our own nature in a sense, and so it's like a cyclic.
It
type
goes two ways, like
of-
everything.
yeah. But yes, it's so that, thank you. Thanks. I don't want to keep too much time. Yeah, I have a lot of questions, but it's I want to give more time for others' question.
There is another question by Professor John, please.
Professor Tosca, I have two questions. One is
Oh, I don't hear.
Non si sente. We don't hear.
Perché la prende da qua.
okay. The first question is according to the slides you presented, is there any issue regarding this black hole entropy and the fact that, in your opinion, quantum mechanics is incomplete? You were mentioning the bad inequalities, and something that we still have to discover about quantum mechanics and the foundation of quantum mechanics. And the second question is, in your opinion, for quantizing gravity, do we need, as many people are saying, to unify all fundamental forces, or gravity is a force that could be quantized in itself, according to different approaches to quantum gravity?
Yeah, the questions about Bell's inequalities. I believe I understand in rough terms what the answer to that is, what the explanation of those inequalities is, and that they are not violating deterministic laws of nature. So I think that people like Bell and others, even in these days, they draw too rash conclusions from what Bell had found. I disagree with that. I think that Bell actually was making some assumptions which, to my mind, are not true. One of those assumptions is called statistical independence, and I think you can't believe in statistical independence. It's just saying that if your system is too complicated to understand, then things should behave in a sort of particularly random way, as if there are no connections. But no, the laws of nature are completely coherent. They are very difficult, but they will not lead to contradiction of the kind that Bell was thinking of. So I disagree with him about those inequalities that they all say that something is not deterministic. I think there is a deterministic world behind everything. And now, what was your second question? Can you repeat?
It's about the other question was about different approaches to quantum gravity. I mean, do you think that we have to unify all the fundamental forces in order to quantize gravity, or gravity can be quantized itself, independent from the other interactions?
Well, I think it's more precise to phrase a problem by saying we want to reconcile gravity with quantum mechanics. That's to say, we want to understand that both theories can be valid at the same time. Whereas gravity could, in principle, be a classical concept. For instance, you can think of a very rough structure, a framework that builds up space and time, and all the details in that framework are controlled by quantum mechanics, but the behavior itself is almost classical. But that would not mean that you need different theories for gravity as for quantum mechanics. No, we need one single set of equations. But the interpretation of those equations might be that it looks as if space and time are very static, very classical. And it looks as if particles are then quantum excitations living on that classical space-time. But then that's only a description of what it looks like. But then if you look more carefully at the equations, you find that there is no difference. That there's no difference between classical objects on one hand and quantum particles on the other. They are described by the same equations, but the mathematics requires a special adaptation for those particles, which it may or may not need for gravity. For gravity, the adaptation you need is something else, which is how to understand that space and time can be curved. That's a very difficult question. Those two conditions are nearly at odds with each other, just not quite. And obviously, our world is described both by quantum mechanics and by general relativity. So yes, there should be a unified framework, but we have to be very rational to be able to find this framework. And I find that most people who are addressing the problem are somehow too much linked to the past of science, in the past days of science, we put symmetry central, we put quantum mechanics central. I believe that you have to basically start from scratch. But that's also not right, because we know a lot about gravity, so it's unwise to start from scratch. But maybe from a logical interpretational point of view, we have to start from scratch. But then, as I said, we should not forget all the things we've already learned about science. For instance, general relativity is a very important findings for Einstein. We should never throw that away. That would be wrong. But we should try to set up a complete system. The belief I have is that black holes have a lot to do with this. Black holes are products of the equations of general relativity and quantum mechanics in a unique corner where they are both valid. And so, if anything, black holes should be able to tell us how to proceed. This has been a very important motivation for people like myself, but also many of my colleagues now, who are investigating quantum gravity by looking at black holes. And so I think that's a very useful way to go, but maybe not the only one. Maybe we also have to look at cosmology and ask questions there, and then see what do we find in common? What do we find about particles that we cannot see because they're at the wrong side of the horizon? What about particles which are at the wrong side of the horizon in the cosmos? The cosmos also has a horizon beyond which we cannot see, because what happens there is outside of our area of influence. So there are horizons everywhere. What do we do with horizons? That's one very fundamental question that both quantum mechanics and gravity have in common.
Thank you so much. There is another question that is a written question by Professor Cannella. He asked, are you conducting experiments to test your theory on black holes that you exposed to us today? Are there any internet links or possibility or known about these experiments, if they are?
Unfortunately, it is very difficult or practically impossible to do experiments on quantum gravity. So what people do instead is they do a Gedanken experiment, a thought experiment. They just imagine experiment and they say, we don't care what comes out as long as it is rational, as long as it makes sense. So we ask, how can we make sense about black holes when they are in the vicinity of quantum particles? And we can ask that question, but unfortunately we cannot actually do the experiment, because The black holes you need would have to be microns in size, but billions of tons in mass. So think of billions of tons of matter fitting in 1 cubic micron. That's very difficult to imagine, but those kind of things you have to imagine. We cannot actually make such things. We don't know how to compress matter to such kind of densities, but still we know what quantum mechanics would be saying, what general relativity would be saying. So all we can ask is make those things coherent, turn the whole lot into one set of equations that describes the complete thing combined. But that's not a physical experiment that you can do in the laboratory, but an experiment that you can do in your mind or in your computer. You just have the computer solve difficult equations. And then, of course, you have the cosmos, the outside parts of the universe. The universe itself, after all, also started as a point, presumably, or very small, very dense. So to get the picture complete, it may be useful to study the debris of the cosmic bang, and the debris of the Big Bang can be seen by telescopes. Maybe those telescopes can still tell us things that we didn't know. I know that they already told us many things we didn't know, but it's very hard to incorporate those in a complete theory. But maybe that's one way in which you should certainly look for experimental observations.
So, what do you think about the possibility of measuring, of observing, between quotation marks, gravitons using the influence of entanglement using the perturbation of entanglement in atoms, for instance, silver atoms or similar atoms.
Yes, but then you can very easily make mistakes, because people like Bill Unruh is doing that. He's looking at the analogon of black holes, but then in acoustics. So sound instead of light. That gives you a factor million, so that makes life a lot easier. But then he has to assume that he knows what happens at the other side of the horizon. In that case, the horizon, in the case of sound, is just you have a sonic boom of an airplane, for instance. But there we know in advance what happens in front of the boom and behind the boom. So we've got all that information, but that's not the kind of information that you have in the case of a black hole. So to liken that to a black hole is a dangerous assumption, and that's what he does do. Otherwise, they're beautiful and interesting experiments, but they might not tell us everything about gravity. So they only tell you the things that you already thought you understood, but they don't say why your understanding might not be correct.
Okay. So, there are other questions. Thank you. There are other questions? No. Okay. Yes, there is a question. Please, come here, because you need the microphone. So another question is from a young student of physics. Please.
I would like to hear your take on the. Can you hear me?
Yes, I hear you.
Okay. I would like to hear your take on the many words interpretation, because you're on the ontological.
So the many world interpretation of quantum physics.
Yep.
Okay.
Yes. To my taste, that is a rather desperate approach, because it says because all the possibilities cannot be excluded, maybe all those worlds really exist, that every moment in space and time the universe splits into billions of other universes where different things happen. I think that to me is a very inefficient way, and it doesn't really tell us what happens, what we will see in our future. So I'm unhappy with that result, with that interpretation, because it doesn't help me. So, and I personally also think it's not needed. You can write theories such that there exists only exactly one universe, not very many. And that one universe develops according to laws that we don't know. But that doesn't mean that all possibilities are realized. That's what the many worlds interpretation wants you to believe. All possibilities actually are realized in some sort of meta-universes. But that the truth of the matter seems to be much more likely what Einstein also thought, and that is that all those possibilities are possible since we don't know any better. Our knowledge of physics is incomplete, therefore all these possibilities are equally probable for us. We can't decide, therefore they are all true. And that's like saying you have this big jar of cookies, you can't decide which cookie you want, so you eat all the cookies to be sure that you have the one that you want is also there. But I don't think that's a very useful way to solve our problems. Actually, it could in principle be right, and I would be very disappointed if it were. I think nature has smarter ways to address these problems than just say that all the cookies have to be eaten because you can't decide. And I think nature does decide. But that's, maybe I'm prejudiced. So yes, we cannot not always be completely neutral in science. Sometimes you have to have some preconceived notion what you think is true. And here I have a preconceived notion. I think there's only one world.
Thank you.
Thank you very much.
Yes. There is another question by the next. So please.
Could you tell us how you think black holes will show us how to proceed toward a unified framework?
Sorry, say it again, this ordinary.
How will black holes tell us how to proceed toward a unified framework, as you were saying before?
Yeah, the question.
Well, it's a very good question because I have no good answer to it at all. Except that black holes give you a corner of gravity theory that you cannot understand otherwise. So it's a completely new corner. It forces us to see how very fast-moving particles interact with each other. For instance, particles come from opposite direction with the speed of light, and then they hit each other with enormous center of mass energy. Now, in the case of the black hole horizon, the center of mass energy is not bounded by anything. So if you take a very early ingoing particle, or a very early ingoing particle, a very late outgoing particle, then the center of mass energy is enormous. It's much bigger than all the energy in the universe, even for a tiny black hole. So that is a branch of science that we do not know at all how to address these days practically. So, but the answer to what happens if two particles collide with that energy is essential to understand the behavior of a black hole. So, knowing that, it seems to me that studying the black hole will tell us something about physics of extremely energetic particles. At the same time, we know there's something wrong with our science today. These extremely energetic particles are not in our universe. We see cosmic rays, but cosmic rays with energies anywhere close to the Planck scale are somehow not produced anywhere in the universe. And that's very curious, very strange. What stops our universe from making even more energetic cosmic rays? And part of the question is that those particles may be extremely rare or something like that. It's something very strange that nature doesn't seem to need those very fast particles. I see that in black holes. We don't need particles that hit each other by energies more than the Planck energy. But why is that? That's not totally obvious. Well, in my equations, I have some ideas about what happens then, that ingoing particles and outgoing particles exchange places some way, and then you can get equations that look interesting, possibly true, but the complete answer to the question has not yet been given. So we are very puzzled by this, and here just studying black holes, making them behave in a consistent and coherent way, maybe the answers come from there, then you'll get a new question answered for free. And that happened before in science. I hope that will happen again.
Okay, thank you so much from everybody. And we greet you, we thank you, and we wish you good work. So, for the next time. Okay.
Thank you very much.
Thank you very much.
Thank you.
So, thanks. And then we see at 2:30. Now we have lunchtime. So it's outside. Thank you, everybody. And see you this afternoon. Bye. Thanks.
Thank you.
Thank you.
Thank you very much. Goodbye.
Bye-bye. We see you after.